So this is just going to be a real quick summary of the difference between normal stress and shearing stress and what stress even is. So to start off, we use sigma for normal stress. Normal stress is going to be force over a specific part of area, and I like to think of it as like squishing or stretching. So if we have this space here as our A, or it could be here, it's just what is our force or normal force, the axial load that is applied over that area. So we've got our sigma stress. One of the ways that I can look at that is just kind of very stressed out dude with a little hat on. So stress, normal stress. So the force is newtons often. So with stress, we can have newtons per unit area, which is meters squared, which is our Pascal. But that's actually pretty tiny. So we usually use kilopascal when talking about normal stress. One of my professors taught us a mnemonic. Kitty hides down under Dad's car motor for remembering the different. So got kilo, hecta, unit, deci, centi, milli. So unit is 1, 10, 10 to the second, 10 to the third. So kilopascal is 10 to the third pascals. And so that is our first introduction. Their angry little stressed out guy. All right, so now we have our shearing stress. And this is, if you can't tell, a sheep. It's a very happy little sheep. So the reason why I say this is because just to help you remember, you shear a sheep and you don't squish them. So you don't have a normal force on your sheep. You have a transverse force to get the wool off without any damage. So we're dealing with transverse forces in this situation. So think of it like taking and pushing to forces against like a brick. And so that area will, unlike when it's squished, have a different type of stress. So there still our regular stress equation. So the average stress is still newtons per meter squared, or kilonewtons per meter squared with kilopascals. And then we have different types of situations. One situation where we have shearing stress is with bolts. So if you picture this is a bolt, and it's holding these sheets together, and they're being pulled in opposite directions. So this is going to create shearing right here. So it's kind of like want to picture it like this. That pull this that way, pull that way. It's going to want to split there. So we have the force over the area, which in this case, if it's cylindrical like that is going to be pi r squared. And then we have a double shear. So with that situation, let's see if I could do this. Oh. So then for our double shear, let's give this is our x-axis. So we'll have this be called FA, this be called FB, and then we'll have FC. So to picture this one, I figured we'll have some more, it's a little bit kind of like that. So slightly different than the other one. And when we're dealing with forces, if you have an object that is not moving, then all of the forces sum out. So FA plus FB plus FC, and we sum force of X is equal to 0, right? So FC is negative because it's going in the opposite direction. And we know that FA and FB are, in this case, the same size force. So that means that FC is equal to 2 FA equal to FB. So when we're looking at just this one space here, or this one space here, then we're looking at tau is equal to FC divided by 2 over area, which is pi r squared. So FC divided by 2 pi r squared. We can get into some of the force summation if that doesn't make sense yet, because I really do enjoy looking at those types of equations where everything is just kind of going back to, you know, if it's not moving, then all of the forces sum to 0. And if it is moving, then we can play with that too. But thank you for watching this first video, and hope this wasn't too confusing.